Cool stars and hot Jupiter exoplanets are not like our Earth. They've got some weird molecules, in particular transition metal diatomics, which happen to dominate the spectroscopy of those molecules. And thus, astrochemists, if they're going to understand these environments, need to have accurate spectral data for what's going on. But these molecules are hard, complex, and though we've had many successes that I'm going to talk to you about today, there have been significant challenges both in the past and moving forward. And I'm going to end with some future directions for this field and how I think that we might be able to tackle the problems that the next decade or two will bring us. I'd like to say thank you very much to my students, Anna Marie Syme and Armando Perry. Some of their work is going to be presented here today. So the first thing to say is that molecular spectral data is really essential for astronomers to interpret their data. So this data represents some of the best data from the Hubble Space Telescope on an exoplanet atmosphere. We can see that there's significant uncertainty in that y-axis, and even on this x-axis, this is over the full spectral region and we maybe have 100 data points. That's not a lot for a spectra, and hence this is a low resolution detection. This data was important because it was one of the first claimed detections of titanium oxide in exoplanets, and because it was this low resolution, there's still significant uncertainty of whether or not it actually is titanium oxide. Astronomers have actually spent quite a bit of time debating, is there TIO, isn't there TIO in hot Jupiter exoplanets? One of the reasons that's really interesting is because it would act like an ozone layer and cause a temperature inversion in the planet's atmosphere. And of course, like most things in astronomy, the answer was wait till JWST launched. And this is a meme from about 2018 or so. But miraculously, Christmas miracle last year, JWST was launched and we've got the first images coming through. For example, my background here, and astronomers have been waiting decades for this image. This is a hot Jupiter exoplanet from the Webb Space Telescope, a spectra. I think it was quite a quick exposure, so hopefully in the future we can expect even higher resolution from this particular instrument. And look, maybe there's TIO there, maybe there's not, we'll see. But while they were waiting for JWST to occur, astronomers got a bit bored and they started to look at all the telescopes that they already had. And they found telescopes from the ground had very bad signal to noise compared to space-based telescopes, but you can make them really big. So the current ones are 30 meters wide, and that means they can have very, very high spectral resolution. And what astronomers learnt to do over the last decade or so is take advantage of that really high resolution. And if you have a template spectra of what the molecular absorption should be, they can actually find it in a mess of noise. They can find molecules, and they've done this very successfully for various systems. So in order to do this, what astronomers need is something called a line list. And a line list is literally just a list of all the energy levels in a molecule and the transition frequencies and intensities between those low vibronic states. And it can be used for a whole range of different applications. The XMOL group at University College London was where I did my postdoctoral research from 2014 to 2017 with Jonathan Tennyson and Sergei Yuchenko. And this is where I first became interested in transition metal diatomics, because of all these molecules here, these were the ones that I was given. And right as I sort of started, there was a paper that came out that said, look, the existing data on TIO isn't good enough. So this is a high resolution transmission spectra over a particular spectral region. This black data is the astronomical observation of an M dwarf, i.e. something that definitely has titanium oxide. And here are 3 different models of titanium oxide using the line lists that were available in 2015. And you can see that they're just completely useless. So there's peaks where there should be troughs. There's just no signal where all the line lists have signal. It's completely useless for this cross-correlation purpose, which relies on aligning one signal with another signal, matching them, and then you have lots of noise, but you get a signal out anyway. And the reason for this is just the extremely high accuracy that was needed here. So this tick scale is 0.35 wave numbers, so they require sub-wave number accuracy. And honestly, ab initio data, nowhere near this accurate. You really need experiment. And that's why this title of this subsection, Pragmatic TIO, comes in. Pragmatism was the way in which I attacked this problem and got a solution that was useful to the astronomers by combining lots of different things. Let me tell you how I did it. So the electronic structure of titanium oxide, really any transition metal diatomics, is extremely complex. So in the visible region's sort of up to about 25,000, ground state up to here. There's 10 electronic states, I think, there. And because the electronic structure is complex, the spectroscopy is complex. So it's not just one electronic band dominating. So for example, here we've got the A to X in green, and we've got the B to X coming through here, and then the C to X coming through here. And then in this lower region, it's a bit of everything. There's lots of different states that you need to get right. And remember, we need to get them right to wave number accuracy. That's hard. And indeed, if you rely on ab initio methods, it's actually impossible. So this is just a selection of transition metal diatomics that I pulled from the literature with, these are high-level quantum chemistry techniques. This is the excitation energy. This is calculated versus the observed transition. And you're off by thousands of wave numbers, just randomly, no real pattern there. There's no method that's any better. You just get a different number. So you can see that if you don't have experiment, you're not even going to have the transition frequency the right color, which is a problem, obviously. When you go to vibrational frequencies, it's a little bit better, but you're still off by 20 wave numbers. This is not sub-wave number precision. We're going to need to do something better. And that something better is we combine it with experiment. So the frequencies from experiment are really, really accurate. But where experiment falls down is the transition intensities from experiment are near impossible to get. From theory, that's really what it excels at. You just calculate the off-diagonal dipole moments between electronic states. I won't say that's easy, but using any of those previous methods, you can calculate it. But isotopologues, on the other hand, are trivial. There's literally a line in the code and I go, I want titanium 46 instead of 48, press run and it's there. Whereas with experiment, you need to do the whole experiment again or use some sort of model that really then takes away the reason why you're doing experiment in the first place. So what does this look like in practice? We do electronic structure calculations the best we can do, mostly focusing on the dipole moment surfaces because they're the thing that you can't get from experiment. And then we combine all the experimental data that we have access to in a single set of experimentally derived energy levels using the Marvel procedure. The Marvel analysis is really important because it's all about consolidating experimental data from many different sources. So for TIO, there's been more than 30 papers that have done some work on TIO. Often they're from the 1960s, 70s, and we need to put them into a digitizer. They're not in a nice supplementary information. And then what we do is we use this program called Marvel, which converts from those assigned transitions to a set of empirical energy levels. You can try it out online. There's the original paper, lots of papers since then. There's been probably 20 molecules that have done a Marvel analysis. This is one of the cornerstones of doing line lists and creating molecular spectroscopic data in the 2020s. You need to do a Marvel analysis and take advantage of all the experimental data, not just the latest paper. We take this information, we put it into a nuclear motion code, and then we construct the examol line list. And using this pragmatic approach, we can get a line list, in particular this Toto green line list, that agrees with experiment pretty well. So remember, this black line is the observations, TIO is here, and it's at least dipping and rising at the same rate. You can see that there's still very much differences, but here the cross correlation will find you TIO, unlike the previous line list examples. The other really nice result from the line list is actually the isotopolog predictions. And let me take you through this figure to show off what we've done. So this is the experimental data here, and you can see that the strong lines are probably titanium-48, the main isotopolog, but all these little lines really look like a bit of noise to me. But what was really cool was when we put the isotopologs in their experimental abundances, you actually see all these little lines match up perfectly with the isotopolog spectra, and they're combining together, and it's just a really, to me, beautiful alignment of the experiment in theory, showing that this simulation is really getting that subwave number accuracy that we're looking for. So now I'm going to take you in depth in the line list construction process as we envisage it now in 2022. First of all, you need to do experimental data, you need to compile them. Secondly, you need to get your ab initio variational calculations, i.e. solve the nuclear Schrodinger equation, see what the best data you can get is. It's really important to note here that we do fit our variational calculations to our experimental data, and I'll show you how we do that in a moment. And the third thing we do that we haven't actually done for titanium oxide yet is add perturbative or effective Hamiltonian energy levels. So these are band constants that are fitted This is generally what experimental spectroscopists use to model their data. And therefore we thought, well, we're using the experimental energy levels, we're using the quantum chemistry variational models. Why don't we use the other ones and then create a tri-hybrid line list where we take each of these sources of information on the energy levels of molecules and then combine them so that we get as many of the advantages and reduce as many of the disadvantages as we can. Let me take you through it. Ab initio data is generated using some high-level quantum chemistry method for transition metal diatomics, and even for normal diatomics, multi-references are kind of useful. The ab initio data gives you the start of what is called a spectroscopic model, which consists of an energy component, which is the potential energy curves and the coupling curves, and the intensity spectroscopic model, which is the dipole moment curves. The spectroscopic model is generated using a standard electronic structure quantum chemistry package such as MolPro is very common in this particular field because of its very high-level multi-reference calculations and its ability to deal with many, many electronic states. These are the curves. It's important that they're smooth. What happens next is we put this solution to the electronic Schrodinger equation into what's called DUO, which is a program that solves the nuclear motion Schrodinger equation and gets us variational energy levels and a rho vibronic wave function. The next step is that you compare these variational energy levels from DUO to experimental energy levels from Marvel, and you'll find they won't match. So what you do is you actually refine the spectroscopic model based on these experimental energy levels. You go round and round and round until you get convergence. This is absolutely critical, and this step has been done for at least a decade. For NH, the ab initio curves and the variational curves match very well. This is not going to be true for transition metal diatomics, but hey, I wanted you to see the ideal. Once the spectroscopic model is producing as close to the experimental energy levels as possible, we say excellent, and we produce a variational line list. Now, this variational line list is not perfect. There are still differences between the experimental energy levels and the variational line list, which is on this y-axis. And they're about on order one wave number for NH. You can imagine the more complex the molecule, the larger this residue is. And that means that it's really, really important, especially for something like TIO, and this was the step that was missing originally, to re-put the experimental energy levels back into the line list. And we're going to call this, in today's language, a dihybrid line list. In the literature, you'll also be calling it a Marvelized line list because experimental energy levels are Marvelized. But why stop here? We've got some perturbative energy levels. Why don't we put those in as well? And normally you put them in, so experimental energy levels are most reliable, perturbative energy levels are the next, as long as you're interpolating, not extrapolating. And then the variational data is what creates the very large number of energy levels. And it gives you all the transition intensities from the variational model. This plot on the left is just to demonstrate that the calculated energy levels have higher errors compared to experiment than the x-axis, which is the perturbative or effective Hamiltonian energy levels. This is why we preference effective Hamiltonian over calculated when we've got the data. And I just also wanted to emphasize something that we've really spent a long time ignoring and not giving astronomers, and that's the uncertainties. So now, within about the last year or so, XMOD line lists mostly have uncertainties. And you can see for Marvel, we know those based on experimental uncertainties. Effective Hamiltonians, we can guess, and calculated, we do the best job we can here. Might be an overestimation, but the important thing is that if it's only calculated, it's probably not going to be very good for high resolution cross correlation. And you can see here that for something like NH, most of the low-lying energy levels are from Marvel, i.e. from experiment, but we're really getting that extrapolation up to higher J, up to higher vibrational numbers from the calculated energy levels. And the effective Hamiltonians in this case are not making a huge difference, but this does vary molecule to molecule. Now, this is a really important plot that we should have produced a long time ago, but Anna, my honours student, introduced it to us, and now I'm sold. And this plot is as follows. It's just the cross-section, i.e. the intensity of the absorption, as a function of wavelength or wave number, depending on what you're most used for. Notice this is a log plot, and the black line underneath here is showing you the total line list, and the yellow line is showing you the Marvel only line list. So at 298 or room temperature, they're pretty much the same. But when you get to 2000 wave numbers, these high temperature, that variational line list can be very important. And in some regions, it's the only source of data. And in other regions, it really is very critical. And this is the same figure for titanium oxide. And you can see here there is significant regions where the MARVEL data is not sufficient, but there are strong absorptions. And this is where you need to be really, really careful of using high resolution cross correlation. I don't in these regions. In this region, you're probably fine. Another way of looking at this information is this plot on the right. Let me take you through it. So on the x-axis, we've got the intensities. And if we consider, for example, this vertical line here at, say, 10 to the minus 17, it's saying that 80 to 90% of the lines are from MARVEL only. So their positions are known to experimental accuracy. These are reliable. But there are 15% of the lines that are not known to experimental accuracy. And they, for example, might be these ones in here where we know that it's not MARVEL that's contributing to that intensity. So we can see for the strong lines, MARVEL is the source of almost all the line list data. And that's why this total and this MARVEL are very aligned at those really, really high intensities. And these weak lines are dominated by those duo, i.e. the variationally calculated lines. And thus we can see that MARVEL is giving us our strong lines and duo is giving us the underlying weak lines, which we know from experience are actually really important because there's so many of them in describing what actually happens in exoplanets and stars. And I just wanted to show another representation of a lot of the data we've looked at. And this figure is showing that the low lying energy levels are normally from experiment, but the high levels that are really contributing to that bulk intensity are from duo and they're calculated. And this is just another representation showing the vibrational quantum number, the rotational quantum number, and each of the, in this case, 12 electronic states that we've modeled in our system. We can see that the low vibrational quantum number, the low rotational quantum number are often experimental, but that bulk of the data is filled out by theory. And we also can see here, just by visual inspection, that some electronic states are known really well by experiment. Some are known quite poorly, like this state here, which if you zoom in is the E state, the B state. They're known quite poorly by experiment. We can represent this information through the uncertainties like we talked about before, and these uncertainties are put in by hand based on our best guess for how accurate we think these various energy levels are. And importantly, you should only use high resolution cross correlation in these really well understood energy levels, say below about 0.1 wave numbers would be perfect. So the next step is to see if this tri-hybrid approach can be applied effectively for a more complex transition metal diatomic, such as zirconium oxide, and that is what Armando Perry is currently doing. And I do want to just briefly show you this data, which shows that the ab initio data in black is not matching that spectroscopically fitted potential energy curve in the solid lines. This is exactly as expected, but does illustrate that it's not going to be quite as simple. However, I've given Armando a challenge. What is the best zirconium oxide line list you can construct in 3 months? What shortcuts can we take? What this is motivated by is within the line list community, we spend a lot of time trying to get the details right. Sometimes those details are important. So the details of putting the experimental energy levels back into the line list to create a dihybrid or trihybrid line list, absolutely critical. But sometimes the details are unimportant. A spin orbit coupling between two states that are very far away does not really matter. Getting the ab initio potential energy curves of, say, zirconium oxide perfectly with ab initio theory doesn't matter because we're replacing them with experimentally fitted spectroscopic potential energy curves anyway. So if you'll permit me for a moment to summarize my perspective on what the future directions for success in this field are, it's collaboration and communication between all the different fields and making sure that we've got the experimentalists talking to the ab initio quantum chemists, talking to the astronomers, talking to the line list creators. Everyone needs to be on the same page and working together. Data availability is going to be critical. The MARVEL spectroscopic analysis, I think, is going to be critical, and having a pragmatic approach for what is the best that we can do right now or in the next short period of time to give astronomers the data they need to make the discoveries that the James Webb Space Telescope, these very massive high-resolution telescopes on Earth, allow them to make the discoveries that will go through our newspapers.